Hi, this is lesson 11 in the use of JASP. Last session, we learned how to read in a data set. And we found that the data set that we were using had some problems with the normality assumption being violated. And today I want to do some basic computations as one way of transforming the data in order to deal with those problems. So let's get started. So go to our three bars, open, and I'm going to go over here to JAS data for videos. It's a library that I have. Here are the two data sets that I have. One is in CSV form. We already learned how to read that in, and we learned how to document it. And so I want the documented one. So I want the JAS file, which I saved at the end of that session. If you didn't save it at the end of your session, you should go back and redo that and save it at the end of the session so that when you pull it up, sex or gender is documented. The zeros and ones are labeled as female or male. Job category is labeled as clerical, accounting, sales trainee, security guard, and so forth. Minority status is coded as non-white, white, and so forth. That's what I'm referring to as documented. Instead of just being numbers, we now know what those numbers stand for, just a very basic version of documenting our data set so we're clear as to what we're working with. Okay, so last time we found that when we looked at salaries as a dependent variable, we were focusing on beginning salary, which was called SALBEG for salary beginning or beginning salary. We found that it violated the homogeneity variance assumption. We found that it violated the normality assumption. And one way of dealing with those violations is to transform the data. And so that's what I want to work on with you for a few minutes right now. The transformations that we're going to do are referred to as the ladder of powers. We're just going to do a portion of the ladder of powers, and I'm not going to go into a high degree of detail, but this is the portion that gets most used in the field of psychology. So the biggest problem that we tend to have in measuring constructs in psychology is to have a lot of scores at the low end of the scale and then fewer and fewer at the higher end of the scale. So you imagine something like drinking behavior, where if you measured like how many drinks a person had in a week, there might be a lot of people with 0, 1, 2, or 3. And then there would be fewer and fewer people who would have 10, 20, 40 drinks in a week would be extremely unusual. So that would be an extremely right skewed distribution. And what you want to do with a distribution like that is to pull the values that are really extremely high in towards the other ones. So here's the transformations that we're going to focus on. So imagine that you have the original score like X. The first transformation and common one is to just take the square root of X, which pulls in the right tail, to take the log of X, which pulls in the right tail even more so. A one that's not part of the ladder of powers, but falls kind of in between the log and the reciprocal would be a ranking transformation. So if you had numbers like 3, 25, 36, and 100, and you rank those, the 3 would become a 1, the 25 would become a 2, the 36 is the third highest score, the 100th is the fourth highest score. So what you notice there is that it's really reaching out at those extreme outliers and pulling them in tightly around the rest of the scores. Then we have what's called a reciprocal transformation, which is basically 1 over x. But it doesn't work to simply do 1 over x, because when you do 1 over x, what used to be your highest numbers now become your lowest numbers. In order to deal with that problem, we basically multiply by -1, and it shifts the scale back to where it aligns with what were previously low scores being the lowest and highest scores being the highest. This transformation starts to shift the tail from being a right tail distribution uh, possibly to a left tail distribution, depending upon how bad the original distribution was. And you can see this even more with the most significant one that I could ever imagine using, which is the reciprocal of the original score, but with the score squared. So if you take 1 over x squared, again, to get that in the right order, you would do a negative sign. So, here's a little table showing how this would work. So if your original score was a 36, the square root of x would make that into a 6. If your original score was 100, it would make it into a 10. So you notice that the larger the score, like 100, the bigger it's pulling that at a faster rate down towards the rest of the score. The natural log makes the 36 into a 3.58. It makes the 100 into a 4.605. So even more extreme. A 36 becomes a 1 over 36. Compare that to 100 becomes a 1 over 100. Now the 1 over 36 is a bigger score than the 1 over 100. But if I multiply by -1, now the 1 over 36 is a big absolute number, but it's also negative. So then the bigger number going from negative to positive, not in terms of absolute, is 1 over 100 times -1. And you get the same thing with the square of that. So 1 over 36 squared is quite a transformation. 1 over 100 squared, very extreme transformation. So how do we do those computations? So what I'm going to do is, here's the data set that we have. And don't go into edit data here. You would think that you would go into edit data in order to make a transformation, but it actually becomes harder to deal with if you are trying to do it through JASP. So if you go ahead and click on this button right here for added a computed column, what we're going to do is we're going to compute the square root of these numbers here in this column. So I'm going to click. I'm going to go ahead and call that square root of salary beginning. So I give it a name, and then I can either do this through R code or I can do it through a drop-down menu. I'm going to start you off by doing a drop-down menu. It's going to be a scaled score. I'm going to say create the column. It's created the column already now with the new name. So this really confused me at first when I first tried it out, because I wanted to put in a whole formula with an equals, and you don't, and this facility does not work that way. It already has the name, and whatever you put in here, it's assuming that this is equal to what's in the box. So if I want the square root, I basically just say, give me the square root of my beginning salary or sal beg. And so that's the computation. If you've done something wrong, you can bring it over here into the trash can and start again. You can also look over here for hints on how to do things, like here it's showing you how to do a log. And I don't see one for a square root, but square root is pretty intuitive. And now we then simply say compute column. By the way, you can look at your R code. So if I go ahead and click that button, it's going to show the R code that goes with it. There I hit the compute button. It computed the square root. It shows me my R code is the command sqrt, in parentheses, the name of the variable. Seems like this program wants you to say what kind of variable it was, so it does a dot scale. That sqrt is really commonly used. That's the same command that you use in SPSS, although there are, a few little tidbits to learn with that. It's the same command that you use in Excel. I believe it's the same command that you use in SAS. So it's a very generic command. Okay, so that's our square root. Let's go ahead and try another one. So I'm going to get rid of this first, and then I'm going to say apply my changes. And now I'm back to my starting point, and next I'm going to do the log. And so I'm going to say LN for natural log, SALBEG. And again, I'm going to go ahead and use the drop down, scale, create column. And now I'm going to go ahead and use my command over here, which says natural log as opposed to log base 10 or log base 2. And take salbeg, and it automatically goes in there where that variable was. If I want to look at the R code, compute column tells me what the code was. Fairly simple. If you want to get the ranking variable, I went into ChatGPT. I said I want a command in R code to be used in the JASP environment to compute the rank order of a scale variable. And it said, here's your command. And so then I worked to figure out that. I took and clicked on copy the code. And I forgot that I needed to close this one out. So apply my changes. Add variable. So rank salbeg. And this I'm going to use R code. Create column. I'm going to plug in my R code, and notice that it says it doesn't know what my variable was called. So I'm going to go ahead and change this data score to rank salbeg. Salbeg scale. Let's see. Put scale there and hope that it works, because I'm not very good with this. And it worked. So here, when I do this, it's showing that a high salary of $72,000 is one of the highest scores with a ranking of 473. So, whereas sales trainees have like 70th highest scores with like 13,500. Let's do the reciprocal. So reciprocal salary began. I'm going to go ahead and use R code this time because this command should be relatively easy. It should just be 1 over salbeg dot scale, but times a minus 1. And there we go. That worked, but it's in these exponent version, so I can manipulate that by adding a bunch of zeros here. And now it's minus 6.17, minus 6.53. That looks pretty good. And one more. I'm going to do the reciprocal squared of sal begin using R code, scale variable, create column. It's created the column. My code would be 1 divided by x, and then for square, just like in Excel, you use a caret to raise that to a squared value, and then multiply times minus 1. Oh, I said x, and it's sal beginning scale, name of the variable, and there you go, but it's in this horrible scientific notation. So if you add about 8 or 9 zeros, maybe a couple more, there we go. So the adding of zeros is just to make it pretty. I mean, make it, a number that's easy to see. It's still going to have the same rank order, so the transformation is going to be the same. So it really has no effect. If you were to look at the nature of the distribution with all the zeros or without the zeros, it would still be the same distribution. Okay, close, and now we've computed variables. And so now you can say File, Save, and it now has these variables in the system, and you're ready to rock and roll with the next lesson. Okay, we'll talk to you next time when we actually use these variables.